Okay, well, good morning, and thanks very much for attending this session. Let me maybe start with a little bit of background, what's sort of the purpose of the session. This is obviously linked to the journal club, which is going to focus on quality of scientific research, which, as you all know, has been questioned over recent years. And there's different reasons for that. There's the quality of the data, which can be poor. There's the quality of the reporting that can be poor. But today I'm going to focus more on the quality of the statistical data analysis. And I'll use mediation analysis as one particular case study. The reason why I'm going to focus on mediation analysis is not so much because I would like to make you really familiar with the topic, but it's really one specific setting where improper statistical methods have grown to become really dominant in applied practice and really widespread. So I'd like to give you a little bit of a reflection on that, and then we'll get back to this in the journal club later on. So first of all, let me just explain what mediation analysis is about. If you look at empirical studies that people use in practice, many of those are basically aiming to infer whether a given treatment or exposure like smoking or a given intervention influence a given outcome. And increasingly many studies trying to go one step further. They also try to gain insight in the mechanism. Why does an exposure affect a particular outcome, or how does an exposure affect a particular outcome? And this is where mediation analysis, a type of statistical analysis, is really focusing on. I'll give you a few examples first, and then I'll talk a bit about how people traditionally approach this type of analysis. And then next I'll talk about particular pitfalls that Tang and Cecilia will link back to in the journal club later on. So I'll give 4 examples that link to my own research. The first one is linked to the LEADER trial. The LEADER trial was a major clinical trial looking at the cardiovascular safety of liraglutide. Liraglutide is a treatment for patients with type 2 diabetes. So the focus of the trial was to evaluate the cardiovascular safety of liraglutide as opposed to placebo on top of standard of care. And quite surprisingly, it was found that the liraglutide treatment actually is beneficial. It reduces the risk of cardiovascular events by about 13%, which was a bit of a surprise. And therefore, the company running the study was asked to investigate more closely, why does the treatment have these cardiovascular benefits? So what the investigators found during the study was that people on treatment tend to lose a few kilograms of body weight, and potentially that could be an explanation why we then see cardiovascular benefits. We also see that they have lower blood pressure when they take medication. That could be another explanation. We see that they have better glycemic control and so forth. And so that there are different potential explanations as to why the treatment may reduce the risk of cardiovascular events. So a mediation analysis would really try and look into this more closely and try to figure out what percentage of the effect of treatment on cardiovascular outcomes can be attributed to reductions in body weight, can be attributed to reductions in blood pressure, or to better glycemic control. So that's one particular example. I'm not sure if I make myself clear, and really don't feel, don't hesitate to interrupt if something is unclear. I'm not sure if people find the pace okay, or am I rushing too much? Okay. The second example that I would like to mention is one from health disparities research. In health disparities research, people are looking to compare health of people with high socioeconomic position, for instance, versus people with low socioeconomic position. And then they raise questions like, is the fact that we see worse health in people of low socioeconomic position, is it, for instance, because they get worse treatments? Again, this type of questions, again, can be addressed using a mediation analysis. The example I want to mention here is related to the Danish head and neck cancer group database, where people with low socioeconomic position were found to have a more advanced cancer stage when they are diagnosed with cancer. That's what you can see here on the picture. So we have socioeconomic position on the left-hand side, and then that has an effect on the stage of cancer at diagnosis. In fact, people with low socioeconomic position tend to have a more advanced stage of cancer. Now, when we really want to understand this association well, then it turns out that the association is complicated because people with low socioeconomic position also tend to have more comorbidities, and comorbidities make sure that they end up sooner in hospital. So if you really want to get a clear idea of the impact of socioeconomic position on cancer stage diagnosis, then we would like to eliminate the effect via comorbidity and look at the remaining effects, which we then call the direct effects. And again, this could be done using a mediation analysis which attempts to disentangle how much of the effect of socioeconomic position cancer stage is explained by different comorbidity between people of low and high socioeconomic position versus how much is related to other things. The third example is one from genetic association studies. In many genetic association studies, people find genes to be associated with multiple phenotypes, and then that raises the question whether this is only the result of indirect effects happening from one phenotype to the other. Let me make that point clear. So the Italian genetic study of early onset myocardial infarction found the FTO gene, for instance, to be associated with the risk of infarction in men below the age of 40. Now, the FTO gene is also well known to be associated with body mass, and that then raises the question whether we perhaps only find the gene being associated with the risk of infarction because the gene influences body mass and body mass influences the risk of infarction. So is this the kind of mechanism that is going on, or do we have any remaining explanation? So also here, the goal is really to know how much of the effect is explained by body mass versus how much of the effect is explained by other mechanisms. And so again, the aim is to disentangle different mechanisms between gene and infarction. And then finally, the last example I want to mention is one related to the MiRoR trial. The MiRoR trial was a big HIV prevention trial, which randomly assigned women to either intervention, which meant that they were given microbicides. This is a vaginal gel meant to reduce HIV transmission, or diaphragm. There were 2 HIV preventive measures that were given to the women on the intervention arm, versus control arm, which means no intervention. So what you can see on the picture on the left-hand side is the proportion of women becoming HIV infected throughout the 2-year study periods. And as you can see towards the end of the study, we don't really see any major difference. In fact, the results are looking slightly worse on the intervention arm as opposed to the control arm. So no effect of the intervention, but if you look on the picture on the bottom right, then you can see the percentage of women who reported having used male condoms at the last sexual act. And there is a very marked difference. In fact, women on the intervention arm tend to use male condoms much less frequently, perhaps because they feel protected by the HIV preventive measures. So part of the reason why we don't see any effect of intervention on the proportion becoming HIV infected may be because in truth, perhaps the intervention is effective, but then it has a harmful effect on reductions in condom use. And this is what I make clear on the next picture. So being randomly assigned to the intervention changes condom use in a harmful way, and that in turn influences the risk or increases the risk of HIV. And what we basically see is this harmful effect mixed with the remaining potentially beneficial effects of the intervention on risk of HIV. So the picture on the left-hand side over here is mixing these 2 pathways. We see the real effects of the intervention mixed with the harmful effects, because women on intervention change condom use, and maybe that is why we don't see any beneficial effects. So the investigators, as you can imagine, were really interested in knowing what would have been the effects of the treatments had condom use not been affected by the intervention. And again, the interest here is in the direct effects. The interest is really in disentangling different mechanisms between exposure and outcome. So in all of the previous examples, what I attempted to make clear is that there is some hope that we can disentangle different pathways that may exist between an exposure and an outcome, hoping to learn a bit better what is really going on. And the type of statistical analysis that is designed for this purpose is called mediation analysis. As you may know, this is very popular, especially in psychology and sociology, but also more recently becoming really popular in epidemiology and medicine. So in this webinar, I'm going to give you a bit of an idea how people approach a mediation analysis, not really with the aim that you're going to start and do your own mediation analysis after finishing the webinar. I just want to give you a little bit of an impression how people approach the analysis. And then I mainly want to focus on how this has come to be misused on a very large scale, just to make you aware that there are really contexts in practice where statistical theory seems to be well worked out, but is in fact not correctly worked out and wrongly used. So let me first explain how do people approach a mediation analysis in practice. So the topic of mediation analysis is pretty old. Already in the early, well, let's say in the 30s, Sewell Wright developed path analysis and structural equation models, and in that context, mediation analysis has started to be used. It became really popular in psychology and sociology as a result of a paper by Barron and Kenny being published, which has been extremely influential. I just checked earlier today, and it's been cited more than 80,000 times on Google Scholar today. And so this is a framework that really dominates current practice. So let me explain to you how the Barron-Kenny framework works. So I'm going to focus on a setting where we have one exposure, X, one mediator. The mediator is a potential variable on the pathway from exposure to outcome that we have data on. I'll call this M, and then finally an outcome Y. So this, I'm not going to show you a lot of math, but this is a little bit of math to show you how people approach a mediation analysis. So first of all, to learn about the direct effect of exposure on outcome. So the effects captured by the red pathway, anything not going through the mediator. To pick that up, people would often do a linear regression of the of the outcome on both exposure and mediator. And then they would call the coefficient of the exposure, they would call this the direct effect. This sort of makes sense because if you think about the interpretation of beta X, it really captures how much the outcome would change if we change the exposure but not the mediator. And so because we don't change the mediator, we're sort of blocking the indirect effects via the mediator. So intuitively, it makes sense that beta X would capture a direct effect. Then to learn about the indirect effect, there is two approaches that are very common. One is to first regress outcome on the exposure alone, because the coefficient beta X prime would then capture the total effect of exposure and outcome. And so if we take the difference between the total effect and direct effects, we would get one measure of indirect effects. Alternatively, what people would often do alternatively is regress the mediator on the exposure instead, and then they would multiply the effect of exposure on the mediator, alpha X, by the effect of the mediator on the outcome, beta M, and so take the product of these two coefficients, and that turns out to be mathematically identical. I'll refer to the first method as a difference of coefficient methods, and the second method as a product of coefficient method. But in this context, they really give identically the same result. So these ideas have been taken forward, first of all, to settings where we have multiple mediators. The example here is related to the Mr. Fit trial, where an intervention was designed to improve or reduce the risk of heart disease by influencing smoking habits, influencing cholesterol and blood pressure. And so if you would like to learn how much, what is the effect of intervention on heart disease through smoking alone, then people would multiply a regression coefficient capturing the effect of intervention on smoking times a regression coefficient beta 1 that captures the effect of smoking on heart disease. Similarly, if we would like to get our hands on the effect of intervention via smoking and then cholesterol and then heart disease, then people would multiply alpha 1 by gamma 1, the effect of smoking on cholesterol, by beta 2, the effect of cholesterol on heart disease. And again, this product of coefficient is then used as a measure of the indirect effect of the intervention via smoking, then cholesterol on heart disease. The framework has also been extended to nonlinear models. So imagine that the outcome was dichotomous, then people would often consider logistic regression, and they would basically do exactly as before. First of all, they would regress the outcome on both exposure and mediator, and the exposure coefficient beta x would then be called a direct effect. To learn about the indirect effect, two approaches are common. Either people would regress the outcome on the exposure alone to capture the total effect, beta x prime, and then the difference between both would be used as a measure of the indirect effect. And this is, for instance, what was done in the health disparity analysis that I mentioned before. I've just taken one sentence from the paper there, and the authors basically say adjustment for comorbidity left the estimates of the effect of socioeconomic position on cancer stage diagnosis unchanged. And so based on this, they conclude that there is not really an indirect effect. So what the authors did in this analysis is they did a logistic regression of stage diagnosis on socioeconomic position alone, and that would give them some coefficient beta x prime. Then they included comorbidity in the regression model, and that would give them some coefficient beta x. And based on the change that they observed, they would conclude that there is no indirect effect in this case. Alternatively, people might combine the logistic regression with, for instance, a linear regression for the mediator. And then, as before, they would take a product of coefficients. They would multiply the effect of exposure on mediator alpha x times beta m, the effect of mediator on outcome, and use this as a measure of the indirect effect. In this context, where the models are nonlinear, this product of coefficient method tends to give a different number than the difference of coefficient method, but the two methods are very common in practice. So this is a bit how the traditional methods work. They're very flexible. They're relatively simple. All that we have to do is run a few regressions and multiply coefficients from the different models. All of it is reasonably intuitive, and that makes the whole framework fairly attractive, as you can imagine. So this is now used on a very large scale. There's a whole research field that is working along these lines, and that is a topic of a lot of scientific papers, textbooks, and software packages that are used on a very large scale today. Unfortunately, the whole framework has very little or no justification, and this is the reason why I've taken this out, because this is like one research field that is very dominant in practice and is seemingly well worked out. But in spite of this, there's very little statistical theory that justifies the whole approach. And so what I'm going to do is talk about three major pitfalls that Tang and Cecilia will pick up later in the journal club. I hope to do this in a bit of an intuitive manner so that you can understand at a hopefully intuitive level that something is not quite right with the whole approach. And hopefully that will prepare you a bit for the journal club. Okay, well, let me then talk about three pitfalls, three problems with the proposed approach. The first pitfall is related to problems of confounding. So whenever we attempt to learn about the effect of a treatment, remember that we should be cautious not to compare apples and oranges. If the treated people are inherently more healthy than the untreated people, then obviously we are making an unfair comparison, and we may find seemingly that treatment is beneficial even when it is not. This is, as you know, why people like to do randomized experiments, because this is ensuring that the treated and untreated people are compatible, and that puts us in a perfect position to infer treatment effects. Unfortunately, and this is a point that people often misunderstand, unfortunately, even when we have a randomly assigned treatment, it turns out that this is not enough to be able to disentangle a direct or indirect effect of treatments. We can, from randomized experiments, we can learn about the total effect of treatment on outcome, but we cannot necessarily learn how much of the treatment effect goes along this pathway versus another. Why is that the case? Well, if we look at the picture here, then to learn about the indirect effect of exposure on outcome via the mediator M, there's actually two things that I should be able to learn about. I should be able to learn about how much does exposure influence the mediator, and this is easy in a randomized experiment because the exposure is randomly assigned, so we can learn about the effect of exposure on mediator by just comparing the mediator between the exposure groups. However, even if the exposure was randomly assigned, we cannot necessarily learn about the effect of the mediator on the outcome. And obviously, to learn about whether there is an indirect effect, we should also know if the mediator affects the outcome. The fact that the exposure was randomly assigned does not imply that also the mediator was randomly assigned, and so there could be confounding of the mediator outcome relationship, even when the treatment is randomly assigned. So very often in mediation analysis, people will argue, oh, there's no issue of confounding because we're working with a randomized experiment. But in fact, in truth, in any mediation analysis, there are issues of confounding because the mediator outcome association may always be confounded. There could always be common causes of mediator and outcome that distort the whole association between both. I'll give you one extreme example, which is a bit artificial, but just to think about an example where we know that there is no direct or indirect effects. I've taken an example where we would randomly assign people over wearing gloves or not. So one group of people is asked to wear gloves all the time, and the other is asked not to do that. I'm going to look at the effect of wearing gloves on the risk of lung cancer, say, and it seems reasonable to believe that there would be no effect. So the picture that I've drawn here is assuming that gloves have no effect whatsoever on the risk of cancer. However, gloves do prevent getting yellow stains on your fingers, and so this is why I have this arrow from gloves to yellow stains. Also, smoking may cause yellow stains on your finger, and smoking influences the risk of cancer as well. So this is why smoking confounds the association between yellow stains and cancer. In fact, even though having yellow stains on your finger is not causing cancer, it's very likely so that people with yellow stains on their finger are at greater risk of cancer because they're more likely smokers. And this kind of bias, this biased impression that we see from data, is also biasing direct and indirect effects. In fact, what would happen if we do a traditional mediation analysis is the following. We would multiply the effect of gloves on yellow stains, which is alpha X. We would multiply this by the association between yellow stains and cancer. And there is in fact an association between yellow stains and cancer, even though there is no effect, no causal effect. The strength of the association also turns out to be the product of the coefficients, gamma m times gamma y. And and that would generally be non-zero, even though from the picture you can see that gloves have no indirect effect on the risk of cancer via yellow stains. So this is an example of hopefully showing you that by ignoring confounding, there is confounding by smoking here. If we ignore that in the analysis, then we would get the misleading impression that gloves have an indirect harmful effect on the risk of cancer, whereas in truth, this is not really the case. Now, this problem, the fact that confounding is an issue in mediation analysis, is an issue that has very long been known since at least the early 80s. But unfortunately, this was not mentioned in the very famous Baron and Kenny paper that I mentioned before, which laid the foundation of mediation analysis, and it has therefore become largely forgotten in applied mediation analysis. Unfortunately, the problem of confounding also turns out to be pretty complicated. So I'm not going to say very much about this, but if you look at the setting here where we have 3 mediators, smoking, cholesterol, and blood pressure, you can see that there's lots of potential common causes. We could have common causes of 2 mediators, smoking and cholesterol, or there could be common causes of a mediator and an outcome, blood pressure and heart disease, or mediators themselves may be common causes. The relation between cholesterol and heart disease is itself confounded by smoking, which is another mediator. And this is, of course, making life a bit subtle to really know what are the confounders, what should we pay attention to. And that's part of the reason also why issues of confounding are not given a lot of attention in practice, because they turn out to be rather complicated. The second pitfall that I would like to mention is a more subtle one, and that is that it turns out that data don't carry information about all the pathways in a certain system. I'm going to look back to the system here where we have 3 potential mediators. It turns out then that data don't really carry any information about the red pathway. How much does the intervention influence the risk of heart disease by changing smoking habits, but not cholesterol and blood pressure? I'll try to give a little bit of an intuitive understanding why data cannot really help you to learn about this pathway. So suppose I want to really understand what does the indirect effect via smoking on heart disease really mean. Well, then on the one hand, if we want to understand this indirect effect, we should obviously allow the intervention to change smoking habits, which then may in turn change the risk of heart disease, because this is all what the pathway is about. So we should allow the intervention to influence smoking habits, which may then in turn influence the risk of heart disease. At the same time, we should not allow this to happen, because if we allow the intervention to change smoking habits, well then in turn cholesterol may change, or blood pressure. And so we are in a situation where on the one hand, we should allow the intervention to change smoking, but on the other hand, we should not allow this. And well, let's say it's probably a bit of a difficult point to really capture very well. But the point is we cannot do both actions at the same time, and this is why we cannot really use data to learn about this particular pathway. The point I'm trying to make is that data carry no information about certain pathways, like the red one here, but even so, a traditional mediation analysis would allow you to estimate it by taking the product of the coefficient, the effect of intervention on smoking times the effect of smoking on heart disease. We can do the calculation, but it turns out that technically there is no justification for why that would give that particular indirect effect. The third pitfall, finally, is related to the extension to nonlinear models. The Baron Kenny paper was all focusing on linear regression models, and it's very tempting to use the same ideas when we use logistic regression or some other nonlinear model. But unfortunately, there's also no justification that would allow people to do that. I'll try to make that point clear by simulating data, by constructing a big data set where we know what should come out, where we know the truth, and then we'll see how the analysis turns out to be. I'll use a little bit of R code, even though I realize that maybe not everyone is familiar with it, but let me just explain what the code is about. First of all, N is going to be 1 million, so I'm just creating a huge sample size so that we have a very big data set and that we can ignore sampling variability. Now I'm generating the exposure X to be a binomial variable with 50% chance of being 1 and 50% chance of being 0. So I'm just allowing X to be randomly assigned. Nothing is influencing whether you are treated or not. I'm just flipping coins basically to decide on who gets treatment and who does not. M is the mediator. It's standard normal. It's not related to the treatment. And so I'm basically generating a setting where the exposure does not influence the mediator. Finally, the outcome follows a logistic regression where the coefficient of X would be 1 and the coefficient of M would also be 1 because we have 1 times X plus 1 times M. So the true setting is there is no confounding because there were no other variables in the game. There is no indirect effect because the exposure is not influencing the mediator. And finally, the true effects of exposure and mediator are both 1. So let's have a look what happens if we analyze the data. With the difference of coefficient method, I would do a logistic regression of the outcome on both exposure and mediator. And not surprisingly, if you look at the output, you can see that the exposure coefficient is about 1, which is more or less what the truth is also giving us. In the difference of coefficient method, we would then regress the outcome on the exposure alone. And somewhat surprisingly, that gives us a different effect of 0.837. So the difference of coefficient method would conclude that there is a difference between the two coefficients from the two regression, that is being minus 0.165. And so it would conclude that there is an indirect effect of exposure on outcome via M. This is very surprising because the real situation that I generated in the data is one that you see in the picture where the exposure is not influencing the mediator and therefore there should be no indirect effects. So this analysis is problematic, and the reason is that if you add a variable to a nonlinear regression model, then coefficients are almost guaranteed to change as a result, regardless of whether there is an issue of confounding or whether there is an issue of mediation. This is a phenomenon that I'm sure you heard Tang talk about before, which is known as non-collapsibility, and which is obviously making the difference of coefficient method problematic. The fact that we see a change in the coefficient could be just an artifact of using a nonlinear regression model. It need not have anything to do with mediation. It need not have anything to do with confounding. So that's a big problem. And a further problem with this method is that if you want to understand what the effect measure captures, it's a difference of 2 log odds ratios. If I just go back, the minus 0.165 is a difference of 2 log odds ratios. So that would be very difficult to really understand what exactly it means. The product of coefficient method has the same issue. How would that work? Well, we would complement the logistic regression with, for instance, a linear regression for the mediator. And then we would take the product of these two coefficients, alpha x and beta m. But also that would be very difficult to understand. Alpha x is a mean difference. Beta m is a log odds ratio. The product of both, I have no clue what it could mean. And so it sort of turns out that what people are doing in practice is they use estimation methods, but it's not very clear what exactly they are estimating and how to interpret the results. So let me just summarize these key points. So the point I want to communicate is that traditional mediation analysis are fairly simple and they can be performed without necessitating intensive training. All that we need to do is fit a bunch of regression models and multiply coefficients. That sounds quite attractive, but there are problems with the whole framework. It's not really clear what these methods are estimating. And so we cannot really understand well how to interpret the results that come out of these methods. And we can also not understand whether these methods are justified. If we don't know what they're estimating, then how could we even justify their methods? That makes these methods deceptively simple, but essentially useless in my opinion. This is a point that was made clear in a revolutionary paper by Jamie Robbins and Sander Greenland. They basically said that what we should do in practice is we should first be clear and define what we mean by direct and indirect effects. And once we can be clear, well, only then we can start developing methods for estimating these effects. At present, the world is a bit upside down. People have methods for estimating, but they don't really know what they're estimating. So the insights by Robbins and Greenland have led to a complete redevelopment on mediation analysis, which has now taken place, and which has been partly reviewed in a book publication by Tyler Vanderwill. I'm not going to explain how that works. This is not really the aim of the webinar, but I just want to give you a bit of an impression how the results from such a mediation analysis might look like. So the pictures here are going back to the leader trial that I mentioned at the very start. Remember, we have patients being randomized to placebo, and the curve basically shows what percentage of people still has not experienced a major cardiovascular event, including death. So if you look at the bottom curve, you can see what happens on the placebo arm. After 1110 days, we see that 87.8% of the people on the placebo arm are still without major cardiovascular event. The top line shows what happens on the liraglutide arm. In the intervention arm, we see that after 1110 days, still 89.3% of patients are without major cardiovascular events. So the contrast between both is the total effect of the treatment. The curve in the middle allows us to disentangle this into a direct and indirect effect. So let me just explain you what the middle curve tells us. It basically tells us, so let me go back first to the setting where everyone is on placebo. Then we have 87.8% without major cardiovascular event. If we now move all these people to the intervention arm, but in doing so, we don't change their mediator, we don't change their levels of glycemia. Well, if we do that change, if we make that change, we would see a slight increase in the chance of being event-free. It would go up to 88.1%. So the contrast between both is capturing the direct effects. All that we do is remove people from placebo to intervention, but in doing so, we don't change their mediator. Going from 88.1 to 89.3 is then capturing the indirect effects. This is showing what would happen if we change people's levels of glycemia from what they are on placebo to what they are on intervention, and that would create a much bigger change in outcome. So we can see that most of the effect of the intervention is really indirect. And so we've been able to explain most of the effect because most of it has to do with levels of glycemia. I didn't explain you how to come to these curves and how to do the calculation. This is a lot more complicated than how the traditional framework works, but it has the advantage of giving relatively simple results that we can communicate graphically and whose validity is also easier to understand. So if we compare the traditional framework that I explained and the more modern framework pointed out by Robbins and Greenland that I didn't really explain, then it's good to observe that we're basically trading simple analysis, as in the traditional framework, simple analysis that basically anyone can do, but whose results are pretty difficult to communicate and justify. We're trading those for more complicated statistical analysis, which are only feasible for researchers that had some training on mediation. But the advantage is that the results are easy to communicate, or at least relatively easy to communicate and justify. In my opinion, this is the right way of doing science. I don't think we should necessarily expect that a data analysis can be approached by anyone. Data analyses are complicated. I don't think we can expect that any researchers can do more advanced analysis like a mediation analysis without doing some in-depth training. I don't think, personally, that there is a problem in a data analysis being complicated. I think most important is that what comes out of the analysis is correct, obviously, but also easy to communicate. And very often in practice, I think that the focus of current statistical analysis is quite the opposite. People often try to come up with very simple analysis, perhaps overly simple, a bit regardless of whether the end result is also easy to communicate and interpret. Maybe some food for thought for the journal club later on is whether or not you agree that this should be the scientific paradigm. Should we either try to stick to simple statistical analysis, or is it justified that we use more complicated analysis when they are needed, but leave them to the people who have the training for them? If that is the right paradigm, how could it work in practice? We do observe that even though there are alternatives for the traditional framework, like mediation analysis, it's very difficult to make this framework really being used in practice. And so any ideas on how we can improve the quality of statistical analysis, I think would be quite valuable to hear either now or later in the journal club. Well, this is basically what I wanted to communicate. If people wanted to have some more information on mediation, there's a few references here, including the book publication by Tyler Vanderbilt. But I think the most important point that I wanted to communicate is that it's good to be aware that there are whole fields of science of how to do data analysis that are built on shaky principles, and that you can easily get the impression that you're doing something quite right, even though some justification is lacking. And I would be good to hear your thoughts on how we can improve the quality of statistical analysis, realizing that we're working with a whole mix of people with very different backgrounds. Thanks very much for your attention. If there's any question, then feel free to raise them.
Hello?
Yes. Yes.
Yes. I just have a small question for you, Stijn, about the fact that you criticize the traditional approach in mediation analysis, and you also say that recently people, developed a novel framework for mediation analysis, and it seems to be more, rigorous than the traditional one. But do you think, the communication is somehow not very good? I mean, all of you may recognize most of the time statistical methodology is very complicated with a lot of details, mathematical details, and do you think also because they are statisticians, they are creating a lot of great works, but they are not trying to communicate it with a non-statistician audience. Is that also one of the reasons why we see traditional but simple dominated?
Yeah, I agree. There's certainly some communication issue there. In the context of mediation, much of the literature has appeared in epidemiological journals, which means it's more accessible than what you'd find in a typical statistics journals, and so in general, I think the uptake of these newer methods has been much better than what we typically see. But still, I think it's going to be a very long way before people, maybe especially in psychology and sociology, where the traditional framework is so dominant and widespread, it seems like very hard to create a big change over there, just because people have grown to be really used to the traditional framework, even though, you know, despite the fact there is no justification. So I'm not sure, and maybe not so hopeful, that even when there's good communication, I think it's still a long way before there could be a real change. So I think it's also a bit related to how used people have become to doing certain things. It's hard to change people when they're used to something, I think. And I think it's also hard to, you know, some of the newer methods are unavoidably more complicated. It's not only a matter of communication. It's also, you know, in the setting with 3 mediators, I pointed out that there could be confounding in different parts of the system, and this is unavoidably making the analysis more complicated. So at some point, if the analysis really becomes advanced, such as when there's many mediators, or when the mediators are repeatedly measured in these more challenging settings, maybe we cannot even hope that anyone can just do these analyses. Maybe it just requires a lot of training. And that's a bit where I'm sort of hinting to in my talk towards the end. Is it acceptable that certain analysis can only be done by people who did training? Is that the right way forward, or should we, you know, how important it is, or how important is it that the people who collect the data can also do the analysis themselves? Is that the right way to go forwards? I'm not sure. So in summary, I think it's a bit of both. There's an issue of communication, but there's also an issue of complexity that is unavoidable to some extent, I think.
Okay, thank you.
This is Maria speaking.
Yeah.
I have a question because I'm not completely sure about the issue, because in this effort of measuring direct effects, as I understand, out of whole effect, I'm not sure the issue is that people, because I've learned that you shouldn't adjust for mediators, but only for confounders. So if you adjust for the mediators, you actually introduce bias, and therefore adjust for the confounders. But I'm not sure if the issue is to ignore confounders and not adjusting for these, or to falsely adjust for the mediators in this.
Yeah, so let me maybe go back to one of the earlier slides. So certainly the advice is not to ignore confounding, quite on the contrary. The reason why people usually advise not to adjust for mediators is twofold. First of all, let me first go here. If I would adjust for the mediator, then I'm basically eliminating the effect via the mediator. That means you're changing the scientific question. If the scientific question is about the overall effect of exposure and outcome, well, then I certainly don't want to adjust for the mediator, because I would be taking away part of the effect. So we would only see the direct effects in the end, which is maybe not what the scientific question is about. The other issue is that, and that's what we see here, if there is confounding of the mediator outcome association, then by adjusting for the mediator, we would introduce bias that we would not have otherwise. So there's two reasons why people don't like to adjust for mediators. Now, if the scientific question is a question about mediation, well, then we have no choice but to adjust for the mediator. So if my question is how much of the effect goes through the mediator, well, then obviously, just because a scientific question involves a mediator, I need to use it in the analysis. So it really has to do with what is a scientific question. If the scientific question is about the total effect of treatment, well, then obviously we keep our hands off the mediator. But if the scientific question is about the direct or indirect effects, then we have no other choice. And then we should be really concerned about confounding, because any common cause of mediation outcome should then be additionally adjusted for in the analysis. I'm not sure if that's answering your question.
Yeah, I think with it really depends on the scientific questions.
Yes.
And,
Yes. Mm-hmm.
yeah. Thank you very much.
Sure.
Yeah, great. So Stijn, thanks a lot. It was really, really important for us to have your webinar about mediation analysis. So yeah, it was great. Thanks a lot. And yeah, see you in 2 weeks. The
Good.
Journal Club. Okay. Thanks, guys.
Thanks all for attending. Bye-bye.
Bye.
Bye.
Bye. Thank you.